Welcome to the Explainer. You know, there are these invisible forces all around us shaping pretty much everything. Today, we're going to decode them, and we'll be using one of the most elegant tools in all of physics to do it. All right, so here's our game plan. First, we're going to get our heads around this idea called flux. Then, we'll see how that one little concept opens the door to a massive shortcut called Gauss's law. And trust me, this law lets us solve some crazy-looking problems, like with spheres and cubes, with almost no effort. It's awesome. So here's the big question, right? How in the world do you calculate a force that's completely invisible? It sounds super complicated, but what you're about to see is how we can take this big, complex problem and boil it down to something surprisingly simple. Okay, first things first, we have to start with this core idea of flux. Don't let the word scare you. All it really is a way to measure how much of something, for us an electric field, is passing through a surface. And you know, the best way to think about this is with a really simple analogy. Imagine the electric field is kind of like a wind blowing. Flux is just how much of that wind is blowing through your window frame. That's it. So check this out. When our window is facing straight into the wind, totally perpendicular, we get the most flux possible. The numbers here show it. It's like standing in the rain and holding a bucket upright to catch the most water. You're getting the full blast. But what happens if we tilt that window? Look, at a 60-degree angle, it's like we're giving the wind a smaller target, and the math backs it up perfectly. The flux gets cut in half. This one idea, that the angle is what really matters, is going to be the key to everything else we talk about today. All right, so we've got a handle on flux. Now, let's put it to work. We're going to apply this to a situation you might actually encounter, the electric field that's created by a big, flat, charged sheet. This is where we start to see the power of this idea. Now, this is super important. We've got to understand the difference between materials. Over on the left, you've got an insulator. The charge is basically stuck where you put it. But on the right, with a conductor, those charges are free to move. And since they all have the same charge, they repel each other, right? So they spread out as far as they can possibly get, which means they cover both sides of the plate. And here's the payoff for that little detail. The formula for the electric field of a conductor is double that of the non-conductor. It's not some kind of physics magic. It's just that the charge has spread out over twice the area, so it creates a field that's twice as strong. Makes sense, right? Okay, everything we've done so far has been leading up to this. This is the main event, the big reveal. We're about to introduce an incredibly powerful new tool, the elegant shortcut I've been promising you. So let me pose a little puzzle for you. Imagine you have a box. You can't see inside it, but you can measure the total electric flux coming out of it. The big question is that enough information to figure out what's hidden inside? And the answer, amazingly, is yes. And the reason is Gauss's law. This is one of the most beautiful ideas in physics. It basically says that the total flux coming out of any closed surface is directly tied to the amount of charge trapped inside it. To put it simply, what comes out tells you exactly what's in. Okay, great law, but how do we actually use it? Well, we use a very clever trick. We don't try to solve messy, complicated shapes. Instead, we pick situations that are really, really symmetrical, like a sphere. And this is where Gauss's law goes from being cool to being an absolute game changer. Okay, let's go inside a hollow sphere that has charge on its surface. Now, we imagine drawing our own little sphere inside it. That's our Gaussian surface. So how much charge is inside our little imaginary sphere? Zero, none. And if the enclosed charge is zero, Gauss's law tells us the total flux has to be zero. And if a flux is zero, the electric field must be zero too. This isn't just theory, by the way. This is why being inside a metal car is one of the safest places to be in a lightning storm. But now, let's step outside the sphere. We draw our imaginary surface around the whole thing. Now, how much charge have we enclosed? All of it. And from out here, Gauss's law gives us this incredible result. The sphere's electric field looks exactly like the field from a single point charge, right at the center. The sphere's size doesn't even matter, just the total charge. And this graph just sums it all up beautifully. Look at it. The field is 0, 0, 0, and then bam! You hit the surface, and it spikes to its maximum value. Then, as you move away, it just dies down, getting weaker and weaker with distance. That's the whole story, right there in one picture. Okay, so we've seen how awesome symmetry is for spheres. Let's see if we can use the exact same logic on a totally different shape. Let's talk about cubes. All right, picture a charge sitting right in the dead center of a cube. Because of the perfect symmetry, there is absolutely no reason the electric field would prefer one face over another, right? It's got to be perfectly even. So the total flux just gets split 6 ways. The flux through any one face is just the total divided by 6. That's it. It's that simple. Okay, now let's get tricky. We move the charge to the center of one face. Now, you got to use your imagination a little. That charge is basically sitting on the wall between 2 rooms, right? It's being shared by 2 identical cubes. So our cube only gets half of the total flux. And for the last one, we stick the charge on a corner. Now think about how corners meet. That single point is shared by, count 'em, 8 different cubes, all packed together. So our one little cube only gets 1/8 of the total flux from that charge. So what's the big takeaway from all this? It's that Gauss's law is this incredible hack. It lets us completely sidestep some ridiculously hard math. All we have to do is ask 2 simple questions. 1, how much charge is inside my shape? And 2, is it symmetrical? If you can answer those, you've basically solved the problem. And that really leaves you wondering, doesn't it? I mean, if a simple idea like symmetry can make invisible forces this easy to understand, what other really complex, gnarly problems out there, in science or heck, even in our own lives, are just waiting for us to find the right perspective to see how simple they really are? Something to think about. Thanks for joining me on The Explainer.